Today, we're setting the stage to uncover the monumental physics and the massive logistics behind how heavy metal machines literally defy gravity. If you've ever looked up and wondered how millions of pounds of steel and cargo are just hurled through the sky at supersonic speeds, well, you're in exactly the right place. We are going to break down exactly how jet engines produce thrust. We're going from the invisible molecules of air being ignited all the way out to the sprawling billion-dollar assembly lines that build these absolute beasts.
Okay, let's dive right into this. 43,000. That staggering number represents the pounds of thrust produced by a single Pratt & Whitney F-135 engine. And that's the exact engine used in the most advanced fighter jet on the planet, the F-35 Lightning II. To put that into perspective for a second, that one single engine produces enough raw power to propel an aircraft to over 1.5 times the speed of sound. But how exactly do you engineer a machine that's capable of containing and directing that much explosive force?
To answer that, here's our roadmap for today's explainer. First, we'll look at the mechanics of thrust. Then we'll go inside the engine megafactories. Third, mastering vertical thrust. Fourth, testing extreme engine power. And finally, we'll wrap up with the future of propulsion.
All right, Section 1, the mechanics of thrust, or the physics behind the power.
While jet engines were invented all the way back in the 1920s, the core mechanics of these air-breathing engines remain elegantly straightforward, even with the massive leaps in modern power. It really all comes down to internal combustion in 4 essential steps. First, the open front of the jet engine takes in a massive amount of air directly from the atmosphere. Second, that air gets compressed. And this is done via a series of spinning fan blades inside the engine, which intensely cranks up both the air's pressure and its temperature. Step 3, once that air is highly compressed, fuel is added and ignited in the combustion stage. This skyrockets the temperature even further. And finally, Step 4, this superheated, rapidly expanding gas reaches the nozzle and is violently expelled out the back. Discharging this incredibly fast-moving jet of heated gas is exactly what produces those thousands of pounds of thrust, propelling the aircraft forward. It's just a beautifully simple concept that's been perfected over decades of engineering.
Moving on to Section 2, inside the engine megafactories. Let's talk about building these beasts.
Now, what's really interesting here is that understanding the invisible physics of thrust is one thing, but actually manufacturing it requires an unbelievable physical scale. Most engines today are constructed, repaired, and revitalized in massive 5,000-acre megafactories, places like the Tinker Air Force Base in Oklahoma. Looking at the major players in this space, the sheer dominance and scale are just staggering. Up top, we have Pratt & Whitney, responsible for that 43,000 pounds of thrust in the F-135 we talked about earlier. Then there's Rolls-Royce. At their super advanced assembly plant in Germany, they build the Trent XWB. Now, this thing consists of more than 20,000 components, and the fan alone has a diameter of nearly 10 feet. It is widely regarded as the most efficient aerospace engine ever developed. And finally, on the commercial side of things, we have CFM International. That's a Franco-American venture producing turbofan engines for roughly 39% of the world's commercial planes. Get this, they complete a new engine every 2.5 days.
So, with 20,000 components per engine, the assembly process sounds completely impossible, right? But aviation expert Sam Ekholm really hit the nail on the head after touring Lockheed Martin's mile-long facility. He said, "You can really think of the F-35 production line as a bunch of Legos." I love that analogy because it perfectly humanizes and simplifies the whole process. At each stop along the assembly line, a different component is added. The pieces are just steadily brought together by an army of specialized technicians until the final product rolls right out the door. But make no mistake, assembling these high-tech Legos requires intense precision. Since dozens of third-party companies produce the various parts, Pratt & Whitney's command center actually has to track the movement of more than 45,000 parts every single day. If even a single bolt goes missing, it can stall the entire operation. To guarantee this precise assembly, Northrop Grumman utilizes something called projection works technology. This literally uses lasers to project instructions directly onto the fuselage, showing mechanics exactly which fastener to use. That one single innovation is predicted to save the company over $100 million. And as for the dull, dirty, or dangerous tasks, well, manufacturers are relying on automated robotic work cells to do things like apply plastic materials over fasteners, which is absolutely crucial for perfectly maintaining an aircraft's stealth capabilities.
All right, Section 3, mastering vertical thrust. How we're defying gravity with the F-35B. So how is all this raw manufactured power manipulated for something like the Marine Corps' F-35B Lightning II, a very unique variant designed specifically for amphibious assault ships? I want you to imagine the physical sensation of 40,000 pounds of thrust keeping a multi-ton jet perfectly suspended in midair. In a conventional flight setup, the main engine exhaust nozzle simply pushes heated gas straight back for forward thrust. Pretty standard, but the F-35B features a massive lift fan mounted directly behind the cockpit. When the jet needs to hover or land vertically, that fan actually rotates downward, pushing roughly 20,000 pounds of thrust straight down toward the ground. Simultaneously, the main engine's rear exhaust nozzle swivels downward to push another 20,000 pounds of thrust to the rear of the aircraft. It's just an awe-inspiring feat of engineering that perfectly balances the jet, almost like a helicopter. Once it's airborne, the lift fan is shut off, the exhaust nozzle slowly assumes its normal forward position, and the jet just rockets away.
Moving into Section 4, testing extreme engine power, ensuring safety and reliability.
Now, before any of these powerful engines ever take to the sky or attempt a crazy maneuver like a vertical landing, they have to endure some grueling evaluations. We're talking simulated flight conditions, severe crosswinds, extreme temperatures, and intense pressures. And this all takes place in a highly specialized facility known in the industry as a hush house. Basically, a hush house is a totally enclosed test cell designed specifically to capture and reduce the deafening noise generated by aircraft engines. Inside this strictly controlled environment, manufacturers and aviation regulators can safely push an engine to its absolute maximum power settings. They study its performance, monitor its limits, and check its noise characteristics, all without causing massive noise pollution for the surrounding areas. It is an absolutely critical step before any engine ever sees service.
And finally, Section 5, the future of propulsion, moving beyond internal combustion.
Let's pivot for a second and see how this all builds toward the future. As the aviation industry moves towards sustainable electric propulsion to cut carbon emissions, Rolls-Royce is actively leading the charge with some highly ambitious green initiatives. It really kicked off in 2020 when they began testing the ACEL all-electric demonstrator plane. Nicknamed the Spirit of Innovation, this aircraft has since become the fastest electric plane in the world. But, that was just step one. By 2029, their target is to fully develop and commercialize the world's first all-electric aircraft engine for regional passenger flights. And looking a bit further ahead to 2035, they're heavily investing in research and advanced energy storage to introduce hybrid electric engines for much larger commercial aircraft. We have covered a massive amount of ground today in this explainer, going from the basic physics of compressing air to 5,000-acre megafactories, all the way to 40,000 pounds of hovering thrust in an F-35. But to wrap things up, I want to leave you with a provocative question to think about. As jet engines slowly transition away from the explosive internal combustion we've relied on for nearly a century and move towards silent, battery-driven electric power, how will the massive 20,000-part assembly lines and the megafactories of tomorrow transform to actually build them? It's a fascinating evolution, and I absolutely cannot wait to see where aerospace engineering takes us next. Thank you so much for joining me to learn how jet engines produce thrust. Keep that curiosity alive, and I will see you in the next explainer.